Okay, let's dive into something today that often feels like it belongs, you know, way out there in science fiction.
Right.
But it's actually the fundamental language of reality. We're talking about quantum mechanics,
It influences absolutely everything.
from the tiniest particles all the way up to like the materials that make up our world.
Exactly.
So our mission in this deep dive is really to unpack the core ideas and maybe some surprising applications of quantum mechanics.
And we're drawing from this great set of sources you've pulled together.
Yeah, exactly. The goal isn't, a heavy textbook lecture.
No,
I mean, we want to cut through the noise, find those really key nuggets of knowledge, and hopefully give you those aha moments.
And it's quite a journey we'll take. We'll see how these foundational discoveries led to some truly astonishing insights,
Yeah.
and how these phenomena, which seem so bizarre at first glance, they're now really at the forefront of technology. And honestly, they challenge how we even think about reality.
Okay, let's unpack this right from the start then. Stepping into the quantum world, you immediately hit this inherent strangeness.
Mm-hmm.
So, unlike a classical object like, say, your coffee cup right now,
Right, I know exactly where that is, hopefully.
hopefully, a quantum particle is described differently by something called a complex wave function.
And that's the first big mental shift, isn't it?
It really is.
Yeah.
Because the norm squared of this function, it gives you the probability of finding the particle somewhere.
So not its definite location, but the chances.
Exactly. And it's not like classical probability, where maybe it is somewhere and we just don't know yet.
Right.
Here, the particle, it genuinely exists as this probability distribution until you measure it.
Which leads straight into, well, one of the most famous quantum ideas, superposition.
Yeah.
Your sources have that great analogy, an electron being simultaneously hard and soft.
Right, at the same time, not one or the other.
Exactly. It exists in a combination of states, could be energy levels, could be other properties, until we look.
And that's where it gets really, really interesting. Measurement.
The act of observation itself.
Yeah. It collapses that wave function.
Yeah.
It forces the particle, kind of kicks it into a definite state. And what's even weirder from the sources is this phenomenon where an electron seems to sort of know about a barrier in its path.
Even if it doesn't directly hit it or interact?
Yeah, exactly. It's like its potential path influences the outcome, even if it never actually goes that way.
Which really brings up this fundamental question about what we can actually know. The limits of knowledge.
So that's the uncertainty principle. Heisenberg's thing.
That's it. You just cannot simultaneously know certain pairs of properties with perfect precision.
Like position and momentum.
Exactly. The classic example. The more precisely you pin down its position, the less certain its momentum becomes, and vice versa.
And this isn't just like our measurement tools aren't good enough.
No, that's the key. It's not an equipment limitation. It's baked into the fabric of reality. It's a fundamental property of nature itself.
Wow. Okay. And this weirdness, it extends to how things actually behave too, right? This wave-particle duality thing.
Oh, absolutely. That's another cornerstone. For ages, people argued, is light a wave or a particle?
Right. Like Thomas Young's double-slit experiment seemed to settle it. It's a ways, makes interference patterns.
It did look that way. But then you have other things like the photoelectric effect.
Where light acts like little packets of energy. Photons.
Exactly. Discrete particles. And it's not just light. Even things we think of as particles, like electrons.
They can act like waves, too.
They do. The Davison and Germer experiment showed electrons diffracting, making interference patterns, just like waves.
So it depends on how you look at them.
Precisely. They exhibit properties of both waves and particles. The very nature of these fundamental entities isn't fixed. It's context dependent. How you set up your experiment determines what you see.
Okay, so how does all this strangeness build up something we actually recognize, like an atom?
Right. How do we get from probability waves in duality to, stable matter?
Yeah. The Bohr model was a big step, wasn't it? An early attempt.
A crucial early step, yeah. Bohr proposed electrons orbiting the nucleus in specific discrete energy levels, like little planetary orbits almost.
And these energy levels, they matched the Rydberg relation. That explained the colors atoms give off.
Exactly. It explained the spectral lines why atoms only emit or absorb very specific frequencies, specific colors of light. It showed energy itself was quantized, not continuous, a huge leap.
But quantum mechanics goes further than Bohr.
Oh, much further. It refines it. Electrons aren't just in general levels. They're characterized by specific quantum numbers, usually called N, L, and M.
And these numbers tell you
Yeah.
what exactly?
N gives you the main energy level, sort of like Bohr's shells. L defines the shape of the electron's orbital related to its angular momentum, and M specifies its orientation in space.
So it's like a unique quantum address for each electron within the atom.
That's a great way to put it, a unique address defined by these numbers.
But there's another property too, right? Something purely quantum. Spin.
Ugh, yes, spin. Absolutely fundamental. And the Stern-Gerlach experiment was the key demonstration.
That's the one with the silver atoms and the magnet?
That's the one. They sent a beam of silver atoms through a non-uniform magnetic field. Classically, you'd expect a continuous smear.
But they didn't get that.
No. The beam split into two distinct paths. Just two.
Wow.
It showed definitively that this property, angular momentum, or spin, is quantized. It only takes specific, discrete values. And even weirder, it could take half-integer values, like 1/2.
And it's not like the electron is literally spinning.
No, that's a common misconception. It's an intrinsic angular momentum, like an inherent magnetic moment. It's just a fundamental property electrons have.
Okay. And that leads to another really important rule.
Absolutely crucial, Pauli's exclusion principle.
Right. What does that state again?
It states that no two identical fermions and electrons are fermions. Particles with half-integer spin can occupy the exact same quantum state simultaneously.
Same quantum address.
Exactly. They can't have the same set of quantum numbers, N, L, M, and spin, in the same atom.
And this is why atoms have structure, why electrons fill up shells.
It's the fundamental reason. It dictates how electrons arrange themselves, filling lower energy states first. That's basically the Aufbau principle.
Although you mentioned there are some exceptions, like with chromium.
Yeah, the Aufbau principle is more a guideline, a rule of thumb. In larger atoms, electron interactions get complicated, and sometimes a different configuration is slightly lower energy. Chromium is a classic example where the filling order is a bit unexpected to achieve a more stable, half-filled shell. It shows there are more subtleties.
And there are even finer details in energy levels, too. Fine structure and hyperfine splitting.
Yes, exactly. Quantum mechanics keeps revealing more layers. Fine structure comes from relativistic effects, how electron energy changes slightly due to its speed. And hyperfine splitting is even smaller, coming from the interaction between the electron spin and the magnetic moment of the atom's nucleus itself. Tiny effects, but measurable and perfectly explained by quantum theory.
So we've gone from single atoms. What happens when you bring billions and billions of them together? How do these rules shape, say, a chunk of metal or a piece of glass?
Right, moving from the micro to the macro. This is where the idea of band structure in solids becomes essential.
Band structure, okay.
When you bring atoms close together in a crystal, their individual electron energy levels interact and broaden out. They form continuous bands of allowed energies.
Okay, bands of energy.
And crucially, these allowed energy bands are often separated by gaps ranges of energy where electrons simply cannot exist within that material.
And this band structure, this explains the difference between metals and insulators.
Directly. It's the key. In metals, the highest energy band containing electrons is only partially filled.
So electrons can move easily.
Exactly. There are plenty of empty energy states nearby they can jump into with just a little energy push, allowing them to move freely and conduct electricity.
In insulators.
In insulators, the highest occupied band, the valence band, is completely full, and there's a large energy gap separating it from the next empty band, the conduction band.
So the electrons are stuck.
Pretty much. It takes a lot of energy to kick an electron across that big gap into the conduction band, so they generally stay put. No free movement, no conduction.
And semiconductors are somewhere in between.
Precisely. They have a much smaller energy gap. So while they might act like insulators at very low temperatures, adding energy like heat or light can excite electrons across the gap, allowing some conduction. That's why they're so useful in electronics. You can control their conductivity.
Okay, that makes sense. Now, there's also Bloch's theorem. What does that tell us about electrons in crystals?
Bloch's theorem is fundamental to understanding electron behavior in periodic structures, like crystals. It says that electrons don't just get stuck localized around one atom. Instead, their wave function takes a special form. It's like a plane wave, like a free electron, but modulated by a function that has the same periodicity as the crystal lattice itself.
So they could sort of propagate through the whole crystal.
Yes, coherently. Even though the atoms create strong potentials, these Bloch waves can move through the lattice.
And this leads to another weird idea, effective mass.
It does, and it's a really powerful concept. Think about trying to push a ping pong ball through water versus through air.
Okay, much harder in water.
Right. The water resists the motion. It feels like the ping pong ball is heavier in water.
I see.
Similarly, an electron moving through the crystal lattice interacts with all the periodic potentials of the atoms. This interaction makes the electron respond to external forces, like an electric field, as if it had a different mass. That's its effective mass.
And this effective mass isn't always the same as a free electron's mass.
Oh, definitely not. It can be larger, smaller. And here's the really wild part.
Yeah.
Depending on the band structure, the effective mass can even be negative.
Negative mass. What does that even mean?
It means if you push it one way, it accelerates the opposite way.
Whoa.
It sounds crazy, but it's a real effect, crucial for understanding how electrons move in certain parts of the energy bands, especially near the top of a band. It also leads to the concept of holes, treating the absence of an electron as a positively charged particle with its own effective mass.
That's pretty mind-bending. Is there a modern material where these effects are really obvious?
Graphene is a fantastic example. It's that single layer of carbon atoms in a honeycomb lattice.
Right. Super strong, super conductive.
Exactly. And its unique, simple 2D structure leads to a very specific band structure where electrons near certain energy points behave like massless particles described by the Dirac equation, similar to relativistic particles. This gives graphene its incredible electronic properties.
Okay. And it's not just the electrons doing things in solids. The atoms themselves move.
Right. The atoms in the lattice aren't perfectly still. They vibrate around their equilibrium positions.
By heat.
Thermal energy causes these vibrations, yes. And just like electron energy is quantized, these lattice vibrations are also quantized.
And the quanta are called phonons.
Phonons, they're like quantized packets of vibrational energy or sound waves propagating through the lattice. Understanding phonons is crucial for things like thermal conductivity, electrical resistance, even superconductivity in some materials.
And they explain things like the Musbauer effect, too.
Yes. The Musbauer effect is a great example. It's where a nucleus embedded in a solid can emit or absorb a gamma ray without losing energy to recoil, because the recoil momentum is taken up by the entire crystal lattice, essentially involving phonons.
Okay, this is getting really deep. Let's shift to maybe the most famously weird quantum thing. Entanglement.
Ah, entanglement, yes.
Yeah.
Definitely up there on the weirdness scale.
So the basic idea is you have two or more particles linked.
Linked in a very special quantum way, such that they share the same fate, the same description, no matter how far apart they get.
So if you measure something about one,
You instantly know the corresponding property of the other one. Instantly. Even if it's light years away.
it's like they have this shared destiny.
That's a good way to think about it. A single quantum description covers both until a measurement is made.
Now, this really bothered Einstein, didn't it? The EPR paradox.
It did. Einstein, Podolsky, and Rosen formulated the EPR paradox to challenge quantum mechanics. They argued it must be incomplete.
Because of this spooky action at a distance. That was Einstein's phrase.
Yeah, that was his phrase. It highlights this seemingly instantaneous influence. Measuring particle A seems to immediately affect the state of particle B faster than light could travel between them.
Which sounds like it breaks relativity. Faster than light communication.
That's the immediate thought, but it actually doesn't allow FTL communication.
Oh, why not?
Because while the correlation is instantaneous, you can't control the outcome of your measurement on particle A. It's random, fundamentally probabilistic according to quantum mechanics. So you know what state particle B is now in because of your measurement on A, but you couldn't use that to send a predetermined message to someone waiting at B. You can only confirm the correlation after the fact by comparing results classically.
Got it. So it's a correlation, not communication.
Yeah.
But it still challenges basic ideas about locality, realism.
Exactly. Locality is the idea that objects are only directly influenced by their immediate surroundings. Realism is the idea that objects have definite properties independent of observation. Entanglement seems to violate one or both.
And this wasn't just philosophy, right? Bell's theorem made it testable.
John Bell's work was ingenious. He showed that if reality was based on local realism, meaning particles have definite hidden properties determined locally, then the correlations between measurements on entangled particles could only be so strong. There's a limit, an inequality.
Bell's inequality.
Right, and quantum mechanics predicted correlations stronger than Bell's inequality allowed. Experiments, starting significantly with the Lane aspect in the 1980s and getting ever more sophisticated since, have consistently shown that quantum mechanics is right. Bell's inequality is violated.
So, what does that mean? We had to give up locality or realism?
Or both. The experimental results force us to conclude that the universe, at its fundamental level, cannot be both local and real in the classical sense. It's a profound conclusion about the nature of reality.
And things are getting even stranger now? There's a new paradox.
Yes. Recent theoretical work extending these ideas. It suggests that if you apply quantum mechanics consistently, even to the observers making the measurements,
Okay.
then you run into an even deeper contradiction. It seems we might have to abandon one of three core assumptions: that measurements have single outcomes, that these outcomes aren't influenced superluminally, or that observers can freely choose their measurements.
Wow, so we don't even know which basic assumption is wrong.
Not yet. It's right at the edge of theoretical physics and the interpretation of quantum mechanics. It forces us to confront just how strange reality might be when quantum effects are fully considered, even at the macroscopic level of observers.
Okay, so turning back to applications. This weirdness, superposition, and entanglement is what powers quantum computing.
That's the core idea. Classical computers use bits. They're either 0 or 1.
Right.
Quantum computers use qubits. Thanks to superposition, a qubit can be 0, 1, or crucially, a combination of both 0 and 1 at the same time.
So one qubit holds more information.
In a sense. And when you entangle multiple qubits, the system can explore a vast number of possibilities simultaneously. 2 qubits can represent 4 states at once, 3 qubits represent 8, and so on. It grows exponentially.
Giving them massive computational power for certain problems.
For specific types of problems, yes. Things like factoring large numbers, which is hard for classical computers, or simulating complex quantum systems like molecules for drug discovery. The potential is immense.
But it's hard to build them, maintaining coherence.
That's the huge challenge. Qubits are incredibly fragile. Any interaction with the environment, heat, stray fields can destroy the delicate superposition and entanglement. That's called decoherence. Keeping the qubits coherent long enough to do a calculation is the major engineering hurdle.
Right. So with all this theory and potential, how do physicists actually see or probe the quantum world? You mentioned scattering.
Scattering theory is absolutely fundamental. It's one of our main tools for interacting with and learning about things we can't see directly.
Like Rutherford firing alpha particles at gold foil.
Exactly. That's the classic example. You throw something you understand, alpha particles, at something you don't, the atom, and see what comes off, where they go, how many bounce back.
And that told him about the nucleus.
Right. So in general scattering, we look at things like reflection. Does the particle bounce off a potential barrier? Transmission, does it go through? And cross-sections, what's the probability it scatters off at a certain angle? And there are theoretical tools, like the WKB approximation, which helps us estimate how particles behave when the potential they're moving through changes slowly.
And for crystals, scattering gives us the structure.
Yes, X-ray diffraction, for example. When X-rays scatter off the regular arrangement of atoms in a crystal, they interfere constructively only in specific directions. That's the Lou condition. The pattern of scattered X-rays directly reveals the crystal's internal lattice structure. It's how we map out atomic arrangements.
And there are other really cool quantum effects mentioned in the sources too, like the Aharonov-Bohm effect.
Ah, yes, that's a fascinating one. It shows that a charged particle, like an electron, can be influenced by a magnetic field, even if travels only through regions where the magnetic field is 0.
How does that work?
It's affected by the magnetic vector potential, which can exist even where the field itself is 0. It shows that these potentials, often seen as just mathematical tools, might be more physically real or fundamental than the fields themselves, a kind of quantum memory of the field.
Wow. And the Barry phase.
The Barry phase, or geometric phase, is another subtle but profound effect. It's an extra phase shift a quantum system picks up when its parameters are changed slowly in a loop. It depends only on the geometry of the path taken in parameter space, not the speed. It pops up in surprising places, like the quantum Hall effect.
And finally, the Born-Oppenheimer approximation. That sounds important for chemistry.
Hugely important. Molecules are complicated. You've got heavy nuclei and light electrons all interacting. The Born-Oppenheimer approximation lets us simplify things drastically. Because nuclei are so much heavier than electrons, they move much more slowly. So you can essentially treat the nuclei as fixed in place while you figure out the electron configuration and energy. Then you can consider the nuclei moving in the average potential created by the electrons. It makes calculating molecular structure and bonding vastly more tractable. It's It's foundational for computational chemistry.
We have really covered a lot of ground today. It's been a true deep dive.
It really has.
From, the probabilistic nature of just one electron, all the way to how they dance together in materials, and then out to entanglement, computing, and these really fundamental questions about reality. You've definitely got a solid shortcut now to being well-informed on some of the most profound and, frankly, weirdest parts of quantum mechanics.
And this whole journey through quantum mechanics, it's really a testament to how knowledge, when we really dig in and apply it, can start to unravel the universe's deepest secrets.
Yeah.
It shows there's always more to learn, right? And that critical thinking is just so vital as we deal with ideas that constantly push against our everyday intuition.
Well, thank you for bringing such a rich stack of sources for us to explore. It's been absolutely fascinating.
My pleasure. And we really hope you listening have had plenty of those aha moments along the way.
Definitely. So, as you reflect on everything we've discussed, here's a final thought to chew on. If quantum mechanics keeps challenging our bedrock assumptions, things like locality, causality, maybe even objective reality itself, what other fundamental principles, things we take for granted, might be the next to be questioned or overturned? And how might that transform your perspective on the universe?